So let's start then with the very basic fundamentals. Gamma rays is electromagnetic radiation. It's very high energy, and it's ionizing radiation. It's potentially hazardous, and it means that it actually changes. It interacts with matter and changes it. It's emitted by radioactive decay. Natural occurring radio elements are potassium, uranium, and thorium, and obviously cosmic radiation. The average crustal abundance is about 2 to 3% potassium, 2 to 3% uranium, and 8 to 12% ppm uranium and 10 ppm thorium. We measured in geophysics with standard scintillation counters in an energy range of 0 to 3 mega electron volts. Everything above that we call cosmic. We measure it as counts per second per energy channel, and obviously what we want to have at the end is ground concentration of the natural occurring radio elements. So gamma ray, as I said, interact with matter by a variety of processes. In the geophysical energy range, Compton scattering is the dominant one, and between the source, which is the ground, and the detector is first the surface material or the source itself, followed by the air column, and finally the detector itself. The emitted line spectra are therefore significantly changed. Okay, so we do see here on the left the line spectra, so it's the potassium, uranium, and thorium line spectra. And in the middle is the flux rate after the gamma rays traveled through 300 meters of air, and if we detect that with our crystals, sodium iodide crystals, then the spectrum looks like we see that on the right hand side. So the left side you would measure in the lab, and the right side is something we measure in geophysics. There is one problem you have to be aware of, is because of the Compton scattering and the air column thickness and the limited energy resolution of the detector, there is a crossover from higher energy peaks to lower energy peaks. That means that the thorium emission does actually have contribute to the uranium and the potassium windows. The uranium emission contributes also to the potassium window we monitor, and if you remove that, you obviously have to remove that, and if the removal of this crosstalk, as I call it, is called stripping. The conventional approach to standard geophysical data acquisition is to monitor 3 or 4, if we take the total count together, relatively broad spectral windows. Potassium energy window monitors the 1.46 MeV peak emitted by potassium, and the uranium thorium energy windows monitor gamma ray emissions from a decay product of uranium thorium, which is bismuth and thallium at 1.7 and 2.2 mega electron volt respectively. We always assume that there is equilibrium in the decay change. So if we measure a daughter product, then we assume that we actually get the concentration of the mother product as correctly as well. This is not always the case, but this equilibrium is a problem. It can occur in the uranium decay series because of radon. So these 3 or 4 windows are generally accepted to measure potassium, uranium, thorium in geophysics. And the total count window gives a measure of total radioactivity or dose rate or whatever we could put it in. So this is a standard spectrum. We have the thorium window, the uranium window, and the potassium window. Thorium peak, uranium peak, potassium peak. Here on the left side, there's a low uranium peak. And if we take all of it together, then it's called, that's what we call total count, the broad window. What you have to be aware of is that on the very low energy side, energy end of the spectrum, sometimes channels or data are not really measured. All the channels are used to store something else. So if you get raw data you haven't seen before, make sure that there is radioactive data or the gamma ray data stored in the early spectral channels, or you have to set it to 0. On a high energy end is very often the cosmic spectrum. The cosmic counts are stored in the last spectrum last channel of the spectrum. Standard spectral resolution is 256 channels, but modern spectrometers count or divide the energy range 0 to 3 MeV into 512 or 1024 channels. So this looks like a nice spectrum, but a real-world 1 second spectrum, as Intrepid would display it, looks like that. That is a random spectra from the Cook-Rad test data, and you see that you don't see much. So just to recap again, gamma rays are measured in counts per second, per channel or per energy channel or per window. So obviously the instrument is mounted on the platform that emits and absorbs gamma rays, and we have environmental changes. So we have to calibrate and correct the raw measured data. The first thing is energy calibration. And energy calibration basically stands for the shift, or with energy calibration, we want to shift the measured peaks where they occur in the instrument to the theoretical peak position. There's dead time. It's the dead time correction, dead time or lifetime correction. We normalize to the nominal sampling rate. We have to remove aircraft and cosmic background. We have to remove the crosstalk between the channels. That's stripping. We have to normalize the air column. That's called that's referred to STP correction, standard temperature and pressure correction. And we have to normalize the ground clearance, which is the height correction. And finally, we have to convert our counts per second into ground concentrations. And there is a very special point that we have to use the radon removal. Energy calibration, specifically old spectrometers that actually are affected by drift, mainly caused by temperature changes of the crystal. So the process to move the recorded spectral peaks to their theoretical position is called energy calibration. Here's an example. Again, Intrepid view from the Cook-Rad spectrum. Look at the red curve, don't look at the blue. The blue spectrum is the raw spectrum. Then we smooth the spectrum, which gives us the red curve, and then energy calibration transfers here. It's very nicely seen on the thorium and the high energy, and it actually transfers the spectrum peak from, this is the channel number, so from 208, there's a peak position, to where it should be at 222. That time is a very simple thing, basically, because the instrument needs a finite time. Usually it's about 10 microseconds to actually process each incoming count. During that processing, the instrument is dead for any other incoming photo peaks or gamma photons, and we have to basically normalize that the actual lifetime to the standard 1 Hz sampling rate. Stripping coefficients are tested or on calibration pads. There are concrete blocks, as you can see on the lower right. The concrete blocks with known concentration of radio elements, and here in that picture you do see a small handheld system tested. You get the stripping coefficients plus the sensitivity coefficients out, but if you put a large aircraft and a large crystal over that and the crystal cannot sit rightly on that pad, the only thing you get out of that calibration is the stripping coefficients, not the sensitivity coefficients. You have to be a bit careful when you do that you're not putting those pads in any highly radioactive environment where dust blows or other sources occur. Aircraft and cosmic background is fairly easy. That refers to the high-level stack. Aircraft spectrum is constant and originates from all matter used to build the aircraft. The main source of radiation is the night vision of the instruments actually in the aircraft, and the cosmic background is scaled with the incoming cosmic counts. So what you do you fly in various in various heights above the ground, preferably water. You don't want to have any radon or dust or any other radioactive material during that high-level stack. So you fly as high as you can, 1 kilometer to 3 or 3.5 kilometers above sea level in an area where atmospheric radon is minimal. So what you get, if you plot basically the window counts, this here is thorium, but it could be any channel or any other windows against the cosmic counts, then we get the cosmic stripping ratios out of the slope from the linear regression, and we get the aircraft background as the intercept time. Here on the right-hand side, you see the heights that were flown, so that's feet. So the bottom one is 1,000 feet, so 300 meter. It goes up to 12,000 feet, that's 3,000 meters, above which the pilots need to have oxygen, so they usually stop at 12,000 feet. So or 3,000 meters height. So again, it's a simple linear regression, and we get our correction factors out, and you can do that for each channel or for window. The next one is the height correction. First, we have to normalize the changing air column under the detector. The first thing is to normalize it, or to bring the density of the air to standard temperature and pressure, and that's very simply done by applying a formula. We have the observed heights, and we have the observed pressure, and we apply this formula, and we then get the height, the standard temperature and pressure height out of that. That's in Intrepid done with dB edit. Then we have to normalize the effect of the varying ground clearance, because obviously the aircraft can't really drape exactly. So there is ground clearance changes from, let's say, 50 meters to 300 meters. In that usual survey height, window count rates vary approximately exponentially with height. And so what we do to calibrate it, or to get the height attenuation coefficients, we fly the so-called low-level stack. That is a series of flights flown preferably over a calibration range, where we do know the ground concentration of the radio elements at a series of heights that reflect the expected ground clearance during survey. And as I said, the window count rates vary approximately exponentially. So we have again a regression curve, but this time we plot the logarithms of the window or the channels per second against the standard altitude and pressure. That's already corrected the height. And then we get the regression line gives us the height attenuation coefficient for the specific channel or window. In this case, it's potassium. Here you see again as the heights, it's much lower than the high-level stack, so that's why it's referred to the low-level stack. Sensitivity calibration is fairly easy. If you have a dynamic calibration range, you basically survey the calibration range at standard survey altitude. And before that, or preferably at the same time, you actually have the ground control or ground measurements, and you just, from the comparison between the airborne data and the ground data, you do get the sensitivity coefficients that are applied to finally get each radio element concentration out of calibrations, energy calibration data at that time until height correction. Everything is in counts per second, and only at the very end. Can you still hear me? Hello?
I can hear you.
You're breaking up a little bit, yeah. It comes and goes for me.
You know, I just got a warning that my internet connection is unstable. So, okay. So, yeah, we all have counts per second, and at the end we do the sensitivity calibrations, and in between there is a radar removal, but that is a special topic. And which I try to explain now. So there are basically two radon removal techniques. The first is the spectral ratio method. and the alternative technique is an upward-looking detector. The spectral ratio method is the standard one we use usually. I'm not aware of any commercial contractor at the moment using the upward-looking crystal, but it is used or has been used. So the spectral ratio method compares the amplitudes of the standard uranium peak at 1.7 MeV to the low energy peak at 609 keV or 0.6 MeV. The contribution and works very simply, or it's not that simple, but with the contribution of the airborne radon, which is basically cloud around the aircraft, to the low energy peak is less attenuated compared to the high energy peak than any contribution from the ground sources. So that basically allows us the estimation of radon, and I'll show you a little bit in the next slide. The other approach is that you have basically a second crystal pack, which is usually smaller, and it's mounted on top of the downward looking crystal pack, and thereby gives the whole assembly a directional sensitivity and is capable of distinguishing between atmospheric radon and terrestrial sources, because they say the larger ground crystals, the downward looking crystals actually block ground, and then everything from any radiation in the uranium channels that are coming from atmospheric radon, which is then assumed to be above the aircraft, is then airborne radon and has to be removed. Both methods require relatively good spectra, and the traditional approach to do that actually is just summing up the spectra over large time intervals, and then you apply the radon correction for that specific time interval. Typically 400 to 600 seconds, or observations are sampled up. The problem with that thing is that in 400 seconds, the aircraft covers approximately 24 kilometers. Radon is a very volatile gas that is pumped into the air by pressure changes. So the assumption that radon concentration is constant over 24 kilometers is a bit, let's say, optimistic. The same is that the assumption that the radon cloud or atmospheric radon is a cloud around the aircraft. It may be below the aircraft, it may be above the aircraft. So radon removal is basically a never-ending story, and it's if there is a lot of radon, you struggle to actually remove it. Low-lying radon, which very frequently occurs in the early mornings, basically sort of small depressions where radon accumulates from the ground, we cannot remove it all. So let's go a little bit back to the standard method, or today's standard method, which is the spectral ratio method. So we have on the top here, this is a plot from an IEA technical document. We have the thorium, uranium, and the potassium peak, and the low uranium at 609 peak. Then the radon spectrum is shown in the second plot. So you do see, and we do try to actually balance the count rates in the low energy window and the high energy window, and compare that to the observed spectrum. And if radon is present, then the ratio between those two peaks actually differs, and that allows us to estimate the radon. The problem with that is that we're looking at a very small window. This is the 609 peak here in the blue line, and the window we use to get it in the dashed lines. And this green curve here is a smooth spectrum already at NSVT smooth spectrum, 1 second spectrum, but you need a very well-defined peak on the 609. The very well-defined spectral shape on the 609 peak to actually apply that, and that is the big problem. And because we do need high quality spectra and we do not want to integrate over more than 20 kilometers, we come to the next. Oh, okay. No, hold on. Forgot something here. What I noticed here on the left side, and as I said, that's an IEA um, uh, plot, is that thorium, potassium, the standard windows are actually counted from 0. Summed up. All the counts are summed up, and in the low uranium window, they sum up, or this plot would indicate that they sum up the counts above the Compton background. So we need to have a good handle on that tiny little peak here. Plus, we probably need to remove the Compton background. This is an attempt by myself to actually calculate the Compton background and remove it. You have in red the original spectrum. Then in green is the calculated Compton background, and in yellow is the difference. So this makes specifically the Compton background removal clears up the low uranium window a bit. The question is whether my Compton background removal is correct or not, but that is something one has to discuss. So because we do need good spectra and we don't want to integrate over too long periods, we come to spectral smoothing. Spectral smoothing actually is the first step of processing, but here for the for this PowerPoint, it's at the end. So spectral smoothing was thought up in the late 90s, and is a process to actually reduce the noise in the gamma ray spectra, and those techniques have significantly improved the quality of process data. There are at the moment, there are two methods currently being used. The one is the NASVD method. NASVD stands for noise adjusted singular value decomposition, and the MNF method, or maximum noise fraction. Both methods use principal component type analysis to extract the dominant spectral shapes and that are present in the raw spectra. So you calculate all the principal components. You have to scale them, but we skip that. And the principal components are sorted according to their noise content, and then the smooth spectra are reconstructed from the first few signal bearing principal components. As I said, spectral smoothing has to be done on the raw data, raw recorded data. So it's basically the first step of our processing chain. It works. Here's an example this is a survey from the mid-90s. On the left side, you see the raw uranium. On the right side, you see the final uranium channel after standard processing, as it was in the mid-90s. If you apply NASVD processing or first spectral smoothing to those data, you get now the very much improved version of the final uranium data. Uranium is always the worst image, and what you see here is that specific. Okay, everything is better defined, and the anomalies are more consistent, but we were also able to remove. These are height busts very likely. We were also to remove those, which the original standard processing people were not able to remove due to basically bad spectral shape or noise in the spectral data. A bit of a discussion. One has to, or a couple of things one has to think about. The question is how doing spectral smoothing is how many principal components are actually required to properly reconstruct the spectra. So standard recommendation is not less than 8 PCs. I always argue that there is only 7 variables because we have potassium, uranium, thorium times 2 due to height variations, and we have the cosmic. So actually we should, 7 spectra, 7 principal components should be okay, but people say 8 or even 10 or more principal components. As said, the standard recommendation is 8 principal components for the reconstruction. In the past, there have been attempts to actually classify the raw radiometric data. You just grid them up after all the corrections and run a classification algorithm over it, and then you apply spectral smoothing with different parameters to each of the classes, which was advertised in the early 2000s or mid 2000s as the solution to all our problems, but it ran into some technical problems and obviously time problems. For instance, how to deal with class boundaries, and then if you have 20 different classes, then you have to run the spectral smoothing over 20 different 20 times, and so on and so forth. What happens if, you know, there are 2 crystal packs. Each crystal pack consists of 4 crystals, 4 liter crystals, and if so, we have 8 crystals, and each of them is basically an instrument in itself. So what happens if one of the crystals is drifting and the others don't? Do we accommodate by increasing the number of spectral principal components, or don't we do that? It's all a thing one has to think about, and we will see in the Cook-Rad spectra are not that good, so we will go into that discussion at the end. But one has to think about what is the best approach. Modern instruments obviously don't have that problems. I didn't see that many. I didn't have that many RSI data from radiation solution instrumentation, or whatever the I stands for. But all these data had absolutely perfect, stable spectra. So coming to the end of the little talk, so we did deal with all the calibrations and corrections. Then we still have to deal with some environmental effects, like we have different vegetations, we have different surface cover, specifically for large surveys. So if a sandstorm blows over, there may be some accumulation of sand, which wasn't there in the neighboring line flown a week ago. Obviously, we have variable surface moisture, but we can't really deal with it. The only thing we do is apply cosmetic methods like leveling, tie line leveling, and micro leveling to you know, even out environmental changes. Last but not least is terrain correction, and Brian Minty actually does have a software to do that, because if you fly in a narrow valley, you get radiation from the side, so you overestimate the ground concentration, or the ground concentration right beneath the aircraft, and if you fly over a hilltop, then you get less radiation from the side, so you underestimate the ground concentration. Brian has a software that apparently deals with it, but I've seen screenshots, but I never had actual data. You still all there with me?
Yes, I'm here.
Okay,
yep.
cool.
We're here.
Yeah,
Yep,
okay, good. So last but not least, error propagation. The radioactive decay is a statistical process, so we get a statistical noise. It's a Poisson distribution, so the noise is basically the square root out of the measured counts per second. So if you have here in the potassium window, if you have 250 counts per second, then you get an error of plus minus 16 or 6%. And if you have 50 counts per second in that specific window, then you get an error of a little bit of 7 or close to 14% error. That through the entire processing step, obviously we have error propagation, and that error propagation can be huge. In potassium, it's from start to basically final data, it's about 60%. Thorium is close to 20%, and uranium uranium channel has a whooping close to 400% error increase, and that obviously is only if all the background calibrations and constants are correct. So you have to keep that in mind. There is a problem. There is a large error. That's why we, for instance, we do get negative count rates. There is no negative concentration. We don't get negative count rates. We do get negative concentrations that do not exist, but due to the error propagation, they are real in the data. So, and as you can see, that's the error propagation is one reason why actually raw uranium images look almost sharper than the final process. You know, the raw on the left, okay, it's stripy, we know that, yeah, but it looks sharper than the final process data, and that is because of error propagation. For QC, quality control of airborne radiometric surveys is a bit of a problem because there's hardly any technical specification. You know, there is what usually is stated is the thorium peak resolution, smaller than 7%. Thorium peak resolution is is basically the full width at half, at half the peak is the full width, and that compared to the actual energy given in percentage is what is the resolution of the instrument. It's energy dependent, so thorium peak on the high energy side has 7%, the cesium peak on the lower energy side with the same instrument at the same quality data is about 10%. So that is actually the thorium peak resolution is one of the standard specifications in airborne radiometric contracts. Some contracts state the ground clearance, but okay, yeah, it's always overridden by the pilots when there is a problem for safety. There's absolutely, or I haven't seen any, there's no specifications for the calibrations. We do a lot of calibrations, and how good all those regression coefficients should be or not is nowhere stated. Then we have the obvious at the bottom, Reinholds operation. Yes, cool. We know that, and then some surveys require repeat line. I don't buy into repeat lines that much because, okay, in Namibia we have very patchy rains, so you know, the repeat line is thought after a rain. You fly the repeat line and see whether the ground concentration are the same, and then we say we can continue flying. But the repeat line is on location X, and 20 kilometers further, it may not have rained whatsoever. My standard thing is, as long as the spectra look good, they do not drift, you know, everything can be fixed by processing. So it's a very good idea to check the sum spectrum per flight, which then could indicate instrument problems. Either it's sort of out of shape, or the peaks are out of location, or it varies. The sum, I do that when I'm doing processing. When I am processing on a current survey, then the sum spectrum is calculated per flight. It's just calculated basically on import as a standard operation, and I have a look at the sum spectrum and then decide, okay, I trust the spectrum or not. The sum spectrum can also be used to calculate the thorium peak resolution. You don't need here the thorium peak specifications that you have to do it prior or post flight. What the people do, they hold some certain welding rods close that contain thorium. They hold it close to the crystals and then record for, I don't know, 5 minutes, or then calculate the thorium peak resolution out of that. But you can do it. You can do it on the sum spectrum as well. The only other channel is also not specified, but you should have a look at it. It's the radar altitude, because it has an influence into the calibrations. And usually we don't have any problems with the radar alt, because radar alt 8 has a very wide footprint, because the instruments are actually made for aircraft safety. So it's very reliable. However, when there is sand dunes and sharply shaped sand dunes, the radar signal may disappear. So if you have a survey over sandy areas, it's a good idea to actually look at the radar altitude as well. But again, it's not specified really in the contracts. So what we're doing in Intrepid, we have that radio it's called Radio 256. It's a spectral processing tool, so that the spectral smoothing until the radon removal. We can do all of that in the Radio 256 tool. SDP correction, as I said, it's just applying a formula, so we do that in the spreadsheet editor, and the remaining the stripping coefficients, the height correction, this sensitivity calibration can be done in standard 3-channel adjust. That gamma adjust is also capable of doing aircraft background and cosmic background and radon removal, but then it's not looking on the full spectra, but only on the window counts. Last but not least, a bit of housekeeping, because we create a lot of channels. So this, we have to stick to a naming convention. Today you have to stick to my naming convention. Whatever you do in the future, it's your naming convention, but get a convention and stick to it. So on the left side here is the tasks and the input and the output. So with that task NASVD only, the input is the channel is the spectrum, 256 channel spectrum, and we output it as spectrum NASVD8 because we will use 8 principal components to reconstruct. So lifetime correction refers to the same naming convention, LT for lifetime, EC for energy calibration, BG for background aircraft and cosmic background generation, and BGRN then for radon removal. To generate output channels and grid them up is only viable or does only make sense after the energy correction, because if you have badly energy corrected data, you may and you generate the standard channels, potassium, thorium, and uranium channels and counts per second, and the spectra is out, then it's just nonsense what's in there. So as from the energy calibration step, we generate output channels following the same naming convention. And there's a couple of visuals. And in the standard 3-channel processing, we input the counts per second here, background and radon, background corrected, background removed, and radon removed, and we get the ground concentration percent in ppm, uranium, and thorium as the output. And again, there's another couple of visuals, and if we have time at the end, we will go back to step 1 and discuss some things that reflect or that influence spectral smoothing. So I guess you're there, you did that, and we could actually start, because the extras, we look at them later. Is there any questions so far?
Not from me.
Nope, not from me.
Okay, cool. So we basically start with all, hold on, I have to get my window right. So we start, come on. Hey. Ah. Okay, so we'll have to navigate to the right directory. Our tasks 256 example. So before we start here, you are familiar with Intrepid in general.
Yes, we are.
Yeah, okay. So basically, just then just click the C0 task, because it's only housekeeping. It takes a bit, and run that task file. Okay, it copies the data and it does do a bit of housekeeping.
Which one was it again? Oh.
It's the first one, C0, prep data task. It copies the data, it kills a couple of calculated channels that we basically start from this clean data set, and when you're done.
Oh, sorry, I'm lost. Sorry.
Yeah, no worries. It's basically prep C0. It's prep the data, and you should end up having. You should And why don't I have that here?
No, it's not
Hold on.
this one. Uh,
Should end up having that Cookrad new data set in your working directory.
mine's still going, I guess.
It's still working, running?
Yeah,
Yeah,
it's still
but
running for
correct.
me. Yeah. Yeah. I was slow, I think.
It takes a bit, but shouldn't take that long because a Cookrad data set is rather small.
Is yours finished, James?
What you might have to do is refresh the folder or just click on another folder and come back to it because it won't automatically appear.
Oh,
Yeah,
okay.
no, I think I started before, after you, so mine's still going.
It gives you a message. You know, once the task is done,
Yeah,
it should give you a
yeah,
message.
a message, yeah.
Yeah, I had
And
to refresh.
Sorry?
I just had to refresh my folder to make the directory, the .dir folder appear.
Visible, yeah. Yeah.
Yeah, mine is still running, James. It hasn't finished yet. Internet slow.
Oh, okay. Shouldn't take that long. Are you sitting in the same room?
No. James working from
Oh.
home. I'm working from the office.
Oh, okay. So just look at your screen here on the top right. If a
I
job
can
file
see
is
it's still,
running, then it's still going along.
it's still going. Yeah,
Oi.
it's still running. That was the C0, isn't it? Yeah, prep data task.
Done.
Okay, if it's gonna slow us down, then maybe you can continue, and then I can catch up, I think.
Yeah, we'll have to look at some things. So you better have the data there.
Okay, but you will be sharing your screen, right? Oh.
Yeah, no, of course, yeah. So, yeah. Do you actually see my? Yeah, you do see my screen, yeah. Of course you
I
do.
see your screen. Yeah, I'm just
Yeah,
thinking
yeah,
time.
yeah,
Sometime we might get
yeah,
stuck because I can
yeah.
always run this again later if I'm not sure why it's taking so long.
Yeah, let's give it another minute or so because it shouldn't be that problematic.
Yeah.
Or you say you're in the office, you're supposed to have
I'm in the office.
a good computer.
Yeah, I know. But it's been particularly slow today, the internet for me.
Or you're not running over a network drive.
Yeah, I'm running from the C drive or whatever. Yeah. It's
So
on my C
it's
drive.
local. It's local on your machine.
It's local.
Not
It is
not
local.
okay.
Yeah,
Well,
it's
then it
local.
should be done. So what are we going to do now?
I think you continue because you share your screen, so I'll just see what you're doing on the screen. I think Adam is doing the same because he doesn't have this stuff with him. Adam, do you?
No, that's right.
Yes. So we'll just watch what you're doing, Raina.
Okay.
That's all right.
So yeah. So
I can see your
okay, so
screen.
the
I can
basic thing.
see your mouse moving.
Yeah.
So
Okay, so it did create the cook route directory. So basically what we do, if you get new data you don't know, you look at them. So we have fields barrow out, which is that is already Elias's set. It's also part of the job. It's the pressure, that we have cosmics, we have coordinates, line numbers, all sorts of things. There's a lifetime. There is a lifetime from spectral original, which is different, but we're not discussing that at the moment. So we have, you know, here's a pseudo flight, and here's the spectrum. So we want to have a look at it. We can do that via the thumbnail, obviously, to see how the survey looks like, or we go straight into 3D Explore. Here we see the survey layout with whatever is displayed here. It's cosmics, okay, doesn't really matter. Survey layout looks okay, except for lines up here don't have, you know, the tile lines don't cover all the traverses. But anyway, what we want to do obviously is look at the spectrum. So at the spectral data, the radiometric data. So we go to, you can go to plot and then create a spectral plot. And since there is only one spectrum available at the moment, it comes up with that, and it's called spectrum. And this is standard 1 second spectra. Unfortunately, there's not much to see in there. We can change it. We can, you know, if we sort of display it only from channel, say from channel 20, we get a little bit more of resolution. But here is something that is the thorium peak. There's the potassium peak. There's hardly any uranium. And we can navigate to the next spectrum. Or this is now the line, or the next row in the line, and also the link works. So we can, if we go to select, then I can, in that overview window, I can go anywhere where there is data, and then I'll see the spectral plot on the right hand side. So although that is a small survey, it's still 20,000 observations, so it's hardly possible to actually, you know, check 20,000 spectrum. So let's just close that down, go to another option of spectral imaging, or imaging the raw spectra. So that is create gamma ray image plots, and that color codes all the spectrum of one line. This is line so-and-so, group 33, and the spectra are color coded along the vertical axis. So you have here channel 0, and you have here channel 256, and you do see all the spectrum color coded here. So that is a nice thing to actually check spectral spectra per line. So if you go to the next line, we just see the spectral that plot changes. So we have whatever it is, 500 or 500 spectra. We can check it in one plot. The problem here is, and I'm sure Intrepid is working on that, is to have guidelines. You want to know whether this is the uranium, the thorium channel, this is the potassium channel, and there is hardly any uranium visible here. But you want to see whether they are in the right position. Okay, so what, and I did see that already, but it's not in the current cut, is that there is little errors here. So the thorium peak should be a 222 channel 222. So this is off the theoretical peak, but for quality control purposes, it actually is horizontal. You know, if that all those peak lines are actually not horizontal, then there is a problem in the spectra, and the spectra does drift, and then the spectra is bad, and then we basically, if it drifts along one line, we can't do anything. You know, then this basically it's a reflight. So, but here you do see it's quite noisy, but as you can expect from the raw spectrum, if you go back again to plot standard spectral plot. I have to move that over. You know, it is a bit noisy, but it's just statistical noise that's within the spectra, and you have to deal with it because we measure only we have a sampling rate of 1 second. Nowadays they go to half a second, I think, so it should be even noisier. So that's how you can check raw data.
Is that the only thing you're really looking there for, Rainer? Is just those straight lines and the drift for each of those peaks?
Yes, basically. I mean, as I said, you can't really do it on the spectrum by spectrum plot because you have a large survey. It's impossible to run it, even if you would have, let's say, you can have it movie-like running through. So you take that plot and you look line by line, or you run through those things here and see whether they are actually horizontal. This here the change in the spectrum intensity of the entire spectrum. Maybe geology, we don't know. We don't care yet. You know, this is just the problem starts if these lines, the peak lines, are too wide or not horizontal. Then there's a problem in the spectrum. And if that is one line, if as I said, if it's not horizontal within one line, then it's a reflight, because that one you can't fix. You know, if those spectral positions change slightly from flight to flight, that's okay. That's still okay. We can deal with it. But if it changes along one line, you just lost. So, but this one doesn't. So this is the way of checking it. And I hope that Intrepid is putting those the guidelines in very soon, that we have sort of a little triangle here, say this is the proper peak position of the thorium peak. Then you immediately know, because with modern data, all modern data I've seen, actually the peak positions are where they're supposed to be. Okay.
Excellent. Thank you.
How is your preparation job going?
Yeah, it's done. It's done now.
It's done. Cool.
Yeah.
All right.
Yeah.
Good. So let's go back to the project manager.
Okay.
Did you? So all the channels are there in your data set? Sorry, I didn't catch your name. What's your? Yeah.
Yvette.
Yvette. Okay, so Yvette,
Yeah.
if all channels are there, so it did do the job. Okay.
Yeah,
so,
it looks like everything is there.
Yeah. Okay, so
and I didn't get any error message. So.
Okay, good. Yeah. No, then so obviously radiometrics, radiometric processing falls under radiometrics. So we have the full spectral processing. This is maximum noise fraction is a separate tool. It's also spectral smoothing. With discussions whether to actually combine it with a full spectral processing, because that's what it is, or not. And at the moment, it still stays as an extra thing. We don't talk about that. It's fairly standard. So we have full spectral processing, and we have the standard 3 corrections. All right. So first step is spectral smoothing. So let's go full spectral smoothing. If you open that up, it gives you a blank window. And under processes, you can select corrections. Oh no, doesn't even the data source has been defined. Okay, let's do it differently. So let's go to C1256 NASVD only task, and right click it, and then open with task. So then we go to it will load the data. You both there?
Yep, so working away.
So processes, we select the corrections, and now you can see noise adjusted single value decomposition, NSVD smoothing is selected, and you can, if you go there, we do get parameters for that specific step. So it's, again, it's NASVD, it's 256, 512, or 1024 channels. It's noise adjusted. Are you familiar with principal component in general?
Yeah, this is
Yep.
currently what we insist on contractors using for our radiometric surveys.
Yeah, but in general, it's that it's because of the Compton background, you know, the low energy end, that's the Compton, because Compton scattering, because of that, the low energy end has lots more counts than just the counting rates, higher counting rates than the high energy end. So you have to scale them. Yeah, each channel you have to scale, and you scale them by unit vector variance, and in the Poisson distribution, that's the same as the standard deviation. So that's where the noise adjusted comes from. So you calculate the noise and then scale each channel by that noise to even out that. Otherwise, the principal component analysis would be dominated by the low energy data, which we don't want to have done anyway. Yeah, because there is no geophysical interest in that. So that's where the noise adjustment comes in. So you can specify a number of principal components to reconstruct. This is 8. We stick with the process with the recommendations. Then we can process the whole thing, the entire data set by pseudo flight. We come back to that later. Process by flight or process by survey. You know, take all the data in the survey and do the principal component analysis. Then the boost signal to noise ratio, I don't even know whether that's working. We just stay away from that, and we can save the spectral components if you want to, and then you know, start from the spectral components and redo it. There's here always a restart from principal component amplitudes when they're already saved. We don't have that, but that's basically all what it can do. The thing is, because of the
Can I just ask, Rainer? Sorry, I'm just wondering, what is the benefit of processing by flight? Would it be better just to process all the data in one by survey?
It says here, initially there was even a processing by line. That was, because it could be done by line, but it's nonsense. Because of the noise adjustment, the scaling thing you have to do first to actually avoid the Compton background dominating all the principal components, or the energy in the principal components. You have to scale that, and that is scaled by noise, and you need a lot of data to actually get that noise estimate correctly. So yes, it could be worthwhile doing it by the entire survey. All right, but there is, we will see that specific. It's actually, I think it was chosen unintentionally, but that Cook-Rad data set actually does have problems. So we come back to that at the very end. How do we do that? There are people saying, okay, here Intrepid put in here 5,000. Some people say you need at least 30,000 values or observations to do that correctly, that you basically see on the data at the end. Then at the moment we do process by flight, assuming that, you know, what can the aircraft achieve. So if it's good, you get 1,000 kilometers per day. So that would be enough observations to actually do the principal component analysis properly, or the scaling properly. But there may also be, you know, a flight that has only a single line. Then you have to really think about it, how to do that. Maybe you put it to the next flight, or that's where the pseudo flight comes in. Pseudo flight is basically just creating an arbitrary flight number from the first 5,000 until that threshold. You can set the threshold till the threshold is reached. So let's say 5,000 points is flight 1, and then the second 5,000 to 10,000 points is flight 2, stuff like that. Obviously, you take the entire line and process it by then. So ideally, with small surveys, you do have a problem. With reflights, you do have a problem. But in general, if there's a full production flight, say 10 or whatever, depends on the line length, obviously, but full production flights over a couple of hours per flight is okay.
Okay, thank you.
Okay.
Yeah.
So is there a minimum of by flight? Like you say, if we have like 1,000 or something per flight, then we can do it per flight. But is there a minimum that you shouldn't, why you shouldn't use it?
Here,
Is there a minimum like
Intrepid,
length? Yes.
No, Intrepid puts in 5,000 for the pseudo flight generation, 5,000 observations to get it. As I said, other people say you need tens or 20 of thousand observations to actually get that right. But if you ask from a terms of reference point of view, you can't say a flight must be longer than X, because then what shall they do if there's a reflight?
Depends.
No, the more the better. But you can't really put, say, a flight must have at least 5,000 observations in the terms of reference. That would be a bit odd. So, you also want to have what I'm doing when I'm processing. On import, I do lots of things, and I do automatically do a NSVD smoothing, because in case I need to have a look at the individual spectra, with the actual unsmoothed raw spectra, I don't see anything. I can't detect the peak. So I do the spectrum on import just for QC purposes, and that's and you have to be for that thing. What I wanted to say, you have to cut the data out to the survey data, because the radiometric is difficult, because the spectral shape changes with everything. It changes with the crystal, and it changes with the flying height, and it changes with all sorts of things. So for instance, what you don't want to have for spectral smoothing is the turns, because sometimes the pilots turn high, so they leave survey height, so you get in the turns. It may happen that the spectral shape actually does change. You don't need the data anyway, so you want to exclude them from the spectral smoothing. You don't take the raw data per flight, from base to base, and then smooth all of them. You only take the survey data. Does that make sense?
Yeah, that's fine.
Okay.
Move on here.
Yeah. All right. So this is the option here that was defined in the task file. So we basically go OK. Then there's other corrections we can do, and at the end we have to identify the output. So, okay, here you can save the spectral data. So here's already the name, the alias is already set to spectrum NSVD8. You can select that, and we deselect all those windows, because we don't want to have any standard window counts out. So you can, select the window, the total count, the potassium, uranium, thorium window, and the low uranium window as an output, and you obviously have to give it a name. We don't want to do that because it's before energy calibration. We just want to smooth the spectrum. So basically that is done, and we can press. It's all okay. We can basically press the apply button, and it's a small data set, so it's okay. Yeah, some nonsense thing. So we wait for it. It actually should be done by now, I hope. Did you both hit the OK button, the apply button?
Yes, I did.
I was
Okay.
just following.
So
I didn't press. Yeah.
Oh, okay. So we just close that, and it should be there. So let's have a look. If you go to the Cookrad new data set, there should be now a new spectrum there. So spectrum NASVD, it's there. So we have a look. But again, going to 3D Explore and create a spectral plot. And this is the standard spectrum. And we want to add one. And this is now the smooth spectrum. And so let's do that from 20 to 20. And we get a bit more resolution in the Y scale. And it does look better. Would you agree that it does look better than the raw spectrum?
Definitely, yes.
Go somewhere, select here, and take another spectrum somewhere out of the thing. There is definite improvement. This is again, there's one thing which is missing, and it's already in, but not in that version. I want to see those guidelines. And I want to see that the thorium peak should be actually here at 222, and that this one is the potassium peak and not the uranium peak. There's unfortunately hardly any uranium in that thing. So in that survey, this is the potassium peak and that is the uranium peak. But there is some, spectral smoothing, it's called. So there is some smoothing in there. We can also verify that by then creating that image plot again. Oops, it's on a different screen. So we have, that's the raw spectrum image plot, and we want to compare it to that. That is now, again, it's an entire line, and it did do a job. It did smooth the spectra component, the spectra. That's basically what it's supposed to do. Question is how good it is. If you look at that, there is at the thorium peak line here is sharper, potassium peak line is sharper, it's less noisy, so it did do a good job. Not as good as I expected it to do, but it did smooth the spectra. Okay, do we all agree?
Yep. Yep.
Okay, so let's.
What about it is not as good as you thought?
Because I've seen individual spectra that are raw and smooth that are better, smoother, basically better defined peaks.
Okay,
and
sure.
The Cook-Rat dataset has a specific problem, and we come to that at the end, and then we can discuss it. But that's okay. It did do a smoothing. It did do it well, and we continue because we don't know anything more really at the moment. So hold on, let me kill all the bloody log files. So we go basically to we did the NSVD smoothing. You could have done. Oh yeah, there's one thing that isn't in the GUI. If you click on that task file, then you see the contents of the task file in the bottom. And that's not in the GUI yet. The first channel and the last channel you can set. And you can set that in the maximum noise fraction MNF as well. As I said in the talk, the very low energy channels are either not counted or not recorded at all, or they're used to store something else, like temperature or something there. And the very last channel is also is often used to store the cosmic. In the preparation of the Cook-Rat data set, I just set all those channels to 0, not to null value, but to 0, that it doesn't the cosmic channel is you get the spectrum, and then suddenly the last channel is a high peak because it stores the cosmic. And here in the task file, you can actually set the first channel and the last channel that is used for the NSVD calculation. It's not in the GUI yet, so you have to do it on the task, but it's supposed to be in the GUI that you can say, no, the first 10 are excluded and the last one is excluded. All right. So we did that. We don't want the pseudo flight. just want to create for lifetime. You know, that is just basically the system records 950 milliseconds per second, so we have to blow it up to 1 second that we can compare it. It's a very simple task, or I'd suggest that we just run that. C2256 lifetime.task, we just run the task file. Because it's nothing you have to input really. So it's a quick one, and it's done. You both with me?
Yeah, I got an error message. Didn't go through.
An
But
error
then I didn't
message.
run. Is it dependent on the NASVD one?
Yeah. Yes. That's why. Where is it here? There it is.
Because if it is, then I understand why my crash, because I didn't run that one. I didn't run
no,
the NASVD.
It's here in the naming convention. Sort of the first thing takes the raw spectrum, which is called spectrum, and puts out the spectrum NSVD8. Then the lifetime takes the spectrum NSVD8, sort of the output of the last task, and then that creates another spectrum. So you have to
I didn't run.
Yeah,
I didn't run the first
order.
task. Okay, that's fine. That's why I got a
okay,
message.
so then you just have to basically follow it on screen.
I will follow. That's fine.
So lifetime is you just have to set the channel to the lifetime channel. Yeah, that's all what you have to do. The energy calibrate task is a difficult one, or it's an important one. Let's put it this way. So we open that thing up, open with task file. So we go back to the 256 channel processing thing. It loads the data set, and the selected corrections are they're too long. Energy calibration. So if you click here, you do see the parameters. James, are you there?
Yeah, I'm just following along.
Okay, cool. So the first thing to detect what it does do, it looks for a peak in the specified bandwidth. So for potassium from channel 107 to channel 123, and then it tries to move it, or it wants to move it to the theoretical position, which is not these channels. So you have to pick these channels correctly, because if you identify them wrongly, they can't detect the peak. So that's where we come to the extras. Just leave that window open, because what I did do is in the extras, if you navigate to this one, extras, and the sum spectra, I actually did create the sum spectra per flight. Okay, so if you highlight that Cook-Rad sum spectrum per flight, there aren't that many data in there. It's 20 odd flights. So again, we open that with 3D Explore. So there is the raw spectrum and the energy calibrated spectrum in there. We want to have a look at the raw spectrum, and we want to have create a spectral plot. This is the sum from all the spectra in flight 1. Okay, and we want to know where those channels here are, because it's not energy calibrated. You know, here's the hold on, sorry. This one is the energy calibrated. EC is for energy calibration, so we want to have the raw, and then it's not energy calibrated. Okay, in order to identify our search windows, that some spectrum help. The raw spectra don't help, because you can't identify the peak properly. So here we can see it properly. We can even boost that up by not showing counts per bin, which is one channel is 11 0.7 keV wide, and this is the count we recorded. We can do it energy per bin, which then boosts the high energy thing. It doesn't have any physical meaning, energy per bin, but basically you take the counts per bin and then multiply it with whatever the energy is in that bin. But it's just a visual enhancement, and now we can basically count where is the potassium peak here. It's basically from 110 to 100, whatever it is. So the peak is here is at 118, 119. So that window here is 17 to 123 is a good search window. All right, similar to uranium, here the search window in uranium is set from 129 to 145. So we have, okay, 129 is probably a bit low, but 145 would sort of get the thorium peak, the uranium peak here. All right. Same with the thorium window, 188 to 221, 188. Again, this is maybe a bit too low, but 221 definitely sees the thorium peak. Okay, because we grab that peak and then we move it to its correct position. You can also set weighting here. There is a problem with the there is a bit of a 501 peak here, so from 43 to 48, but it doesn't see that peak here. So I give it a low weighting. There is lots of potassium in there, so we give it weighting of 1. There is not that much uranium in there, so I gave it a weighting of 0.5. And thorium is a nicely defined peak, so it gets a high weighting. And then you can obviously use user-defined window, but not doing that at the moment. And so energy calibrate by integration period, not by line, by integration period, and then we press OK. And then we want to have here, we want to have the spectrum NASAD lifetime corrected and energy calibrated as the output. Because we did do the energy calibration, we can actually calculate standard windows, total counts per second, or that would be raw basically, total raw, potassium raw, uranium raw, and thorium raw. You don't need the low energy, the low uranium window. So basically, we can hit the apply button. Okay, processing completed. It tells me that. So we can close all those windows, even the standard, that calibration spectrum we don't want to see. Go back to our our working directory. And we'll see there's now spectrum NSVD8, lifetime corrected, and lifetime corrected and energy calibrated. There's a oh no, so it needs the radon removal. So let's have a look at that. Again, go to 3D Explore and let's have a spectral look. Spectral plot. So let's see here, it's the smooth spectrum. Let's compare that to the smooth spectrum, lifetime corrected, and energy calibrated. Oh. The energy calibration didn't work. You see that?
Yeah, how do you know?
Yeah. No, yeah.
Mine looks the same as yours.
Yeah. The energy calibration, so you can zoom in here. Thorium window is always good. So there's there's a lifetime correction, but there is no energy calibration because it is it's not moved. You know,
it should be shifted across to the right, shouldn't it?
Should be across. So okay, let's close that all down.
It looked like it worked when it was in the Sum Spectra folder, but not in this one.
Yeah, maybe we just run that again. And straight from the task file, C3 256 energy calibrate task file, just run task file. Let's see whether maybe I hit the wrong button somewhere. So this one is done. Then let's have a look again. Maybe I did something wrong in the GUI. So now we have here, the smooth spectrum and the smooth lifetime corrected and energy calibrated task. So the lifetime correction actually makes all those data where there is a lot of counts a bit higher, and the energy calibrated to the right position. I don't know. Maybe I hit the wrong button in the GUI.
Yeah, it worked for me this time as well.
This one, yeah. So whatever. Sorry for that. But okay, that worked. So yeah, okay, it did work. So we can close that again. And next task would be the radon removal. So let's again open that with the task. Oops, needs to load the data set. Select corrections. So we have radon removal. If you go into the theory of radon removal, I'm sure you have all the papers for Minty somewhere there. There is a description of this C1 to C
parameters. Yeah.
I don't change them. I tried once and I don't change them. So background the radon. Oh, hold on. We forgot one thing. Sorry.
Is this the cosmic one?
Yeah, we need to do the cosmic one.
Cosmic
we need to run that. Yeah. So cosmic first. Yeah, sorry, my bad. What it does do is it needs a cosmic calibration file because we do a full spectral removal. These cosmic radon JWF ASCII data that comes with Intrepid as an installation. Basically, that calibration files need to be supplied by your contractor, but we use that one, and then we just remove basically the cosmic and the aircraft background, which is applying a slope and an intercept time. So I suggest we just run the task file here because it should be fast. There's not much going on, not much things you can change. So that is done. And then we can go to the radon removal. And I don't know, it's 8:30 already. It's 4:30 your time. So let's just run the radon removal task also as, just run it as a task. So that one is done. Are you at the same stage?
Yep, I just ran both task files. They look like they completed.
Yeah. Okay, so let's have a look. That's already preset. View radon removal channels. So we open that with the task file. It opens up 3D Explore, and it shows us basically the 4 channels. There is 3 channels. There is potassium, counts per second background removed, the aircraft and cosmic background removed, and the radon removed in red. The same for uranium and the same for thorium. You obviously don't expect much going on in the thorium channel, but you would expect something going on in the uranium, that is the main channel, and the potassium channel as well. So if we can now run through through those lines, and we do see just different differences basically between. So there's more that the software estimated more or less radon along those lines. There is one line here starts off. It didn't see any radon, but that could be. If there is no radon, it doesn't see the radon, so it can't remove it. There is more. So yeah, it's just a control plot. We can leave that, and we can see the correction spectra. So let's again open with the task file. Oops, I don't want to have a spreadsheet editor. Oh, sorry. It just creates differences between the one and the other. So we have to run that. It's a DB edit task. So we have to run that. It just creates a difference between the input and the output spectrum. And what I wanted to show you is view spectral changes. That one we can open with the task file. Again, it goes into 3D Explore, and oh, hold on, it was too quick. Didn't do the DB edit task, so we have now here, that's a background difference, one spectrum by the other channel per channel, and we should get the radon differences as well. Oops, hold on, I want to have it in a different plot. So you both see that?
Yes.
Yeah.
That is basically the difference. The difference, if we go to the task file here, is the difference between the lifetime and energy calibrated spectrum and the lifetime energy calibrated and background and aircraft and cosmic background removed spectrum, and the other one, the radon diff, is the difference between the not radon removed and the radon removed spectrum. Okay, so that we do see here. So that's the background diff is up there, and the radon diff is down below there, and that actually is depending on the calibration spectra. And the calibration spectra are in here as well. Should be under databases. So Intrepid calibration spectra. So if we again have a look at that and open that thing up, then there's heaps of calibration spectra. So what we are looking for is the cosmic radon JWF. So there is a cosmic, there is an aircraft. The standard is also the aircraft, and there's a radon spectrum. So we can actually have a look at that, create a spectral plot. So this is the first one is the demo. Oops, come on. Oh, row and group. That is the cosmic. Okay, hold on. Let's go from 10 to 256. So first one is the cosmic. It's just a spectrum that is removed. And second one is the aircraft spectrum. And if you look at our other plot here, this is the background difference, and the cosmic is very small, obviously, but the aircraft is quite large. Then we have all those peaks here. They are removed. That's the difference. Okay, they are a bit smooth because we're using smooth versions, but that is the difference. And now here comes the crux or the problem of the whole matter. Is the aircraft spectrum in the right position, or do they have to be energy calibrated as well? And we have to be careful because we are removing an entire spectrum. We scale it by something, whether it's the cosmic stripping ratio or the aircraft background, which has a scaling. We just remove that aircraft, the measured aircraft spectrum. So if the input spectra is energy calibrated and the calibration spectra is not energy calibrated, or vice versa, then there's a problem. You with me?
Yes, I think so.
And that's a couple of the extras here, because this is a tool I wrote ages ago, just because I wanted to have those lines. And hold on, let's pop that up. Display settings, swap. So this is the cosmic calibrate. It's normalized. Don't bother about worry about the Y scaling. But this is a cosmic spectrum. Here you do see there's something there in the last channel. That's what a cosmic spectrum is supposed to do. There's not much we can see. The only thing I don't believe really is that strong. That strong increase at the low energy, but yeah, okay, it's out of the geophysical use, so we may not use it. The aircraft spectrum is problematic for me because you see here there's the thorium window, the thorium peak, and the uranium and potassium peak, and the windows are marked with the dashed lines. So okay, there is hardly any thorium in that aircraft, but it's definitely not in the right position. There is hardly any uranium in that aircraft, but it's, or there is a bit of uranium in that aircraft, but it's not in the right position. Potassium, the same story. Low uranium is wrong. So are we doing the correction correct, or are we not doing that correct? And if I look at that specific aircraft spectrum, I would say, no, we're not doing it correct. The radon looks okay. You know, radon doesn't radiate into thorium, but it's so short of is here on the it looks like a proper radon spectrum in the uranium channel. The lower energy uranium channel is a bit out, but it's there and almost in the right position. So if you do the full spectral processing by removing a spectra, you have to check a calibration spectra. You have to check the calibration spectra. And I remember once I had energy calibrated one of those spectra because I didn't like it, and you just basically duplicate the one spectra because the calibration spectra is only one spectra, so you duplicate it by 1,000 times and let that energy calibration tool run over it, and then you're sure that the calibration spectrum is also energy calibrated. You know, that is and it's nowhere specified in technical specifications, and it's difficult to get the contractors to get you the calibration spectra. They duck and dive and moan, and so
so if you get that this sort of, you know, like that aircraft spectra that you said, it doesn't look like we're doing the correction properly, we're doing the calibration properly. If you get something like that, what should you do?
I just said you can energy calibrate you have to check it first. Then you can energy calibrate the calibration spectrum. For the radon spectrum, I'm not absolutely sure. Radon, I don't even know how they get the radon spectrum. I think that's done in the lab, and I guess you have to ask Brian Minty how they get it. You know, he sits in camera. He actually sits close. Is he still in camera?
Yeah,
I don't know.
Yeah, we're in touch with him. We are in touch with.
Oh, okay,
Brian,
cool. Yeah. So you can how they get the radon spectrum, I don't know. But it's a major pitfall. And you know, when I was running that Cookrad data, I thought initially, oh, crap data, but then I thought, well, it's a good training exercise because it does show pitfalls. It doesn't really. It is not good data, and it's working. It's not working properly. But this calibration spectra is a pitfall, and that plot here, look at the differences. Obviously we remove a spectrum, or in the case of the background we remove two, the cosmic and the aircraft spectrum, so you do get that the shape of that spectrum out, and that is wrong. You know, the radon may have that looked okay, as we've seen here on the PowerPoint plot. The radon is almost okay, but the aircraft is definitely out. On the other hand, I mean, it's not that much of a problem because aircraft is a constant, yeah? And obviously, you being GA, you want to have comparable data sets, but I merged your grid merged all of Namibia, and they were all calibrated on our dynamic calibration range and blah blah blah. Everything done basically to the book. And if you look at this, you know, grid merge for radiometrics, you apply a scale and shift first. If you look at those statistics, it's frightening. So the aircraft that we subtracted the wrong aircraft spectrum or slightly wrong aircraft spectrum doesn't destroy the data as such. You know, it's not correct, but it doesn't destroy the data. But this is just to show you there is a potential pitfall. If you do QC and whatever the contractor is doing, whatever they applying, which method they apply, they should show you the calibration spectrum, and you have to have a look at them. All right, that's basically the point. Okay.
Okay. Yeah. Thank you.
Yeah. Yeah. So let's close that all down. Error adjustment. Okay. Let's close that all G3D Explore down. We go back to our 256 tasks, and we did the radon removals. Okay, we did that. View all stages. It's again, we can run that and now open with the task file. It again pops up into 3D Explore and shows us all different spectra. The more spectra there are, the longer it takes, but basically that's what you can have a look at it. That's basically the evolution, and let's zoom into the thorium window here at the end. So we have the raw, then we have NASVD, then we have the lifetime corrected, so it's a little bit higher, and we shift it all to the correct peaks, and then we remove the background. There obviously is something, and we remove the radon, which is the last one. Is there. So that is basically spectral evolution. Again, can go somewhere, go to another line, have a look through that. But okay, so that is what the processing did do so far. Last but not least, we do the 3 standard channel processing. So we do the Compton stripping. You know, if you so we don't do that time. You can do it here as well with basically now we leave the full spectral world and go into the window mode. So potassium is from channel X to channel Y, and uranium from channel X to channel Y. So here we could also do dead time and lifetime correction. So we just all set to false. We don't do that. Dead times is all commented out. We do a Compton stripping, that is alpha and negative alpha and beta. That values get on the reverse one, the values you get from the PET calibrations. The contractor will give that to you. It's just the value you apply. Same as the height attenuation. It's the thing you get from the low-level stack flight out for potassium, uranium, thorium, and total counts. And height limits 10 to 200. You can set that, and then sensitivity coefficients are okay. Here, the total count is not calibrated to dose rate, but the counts per second per percent potassium is whatever the values is, 45, 6, and 3. And you can run a smoothing window over it, but it's commented out. So we just run that thing, the task file, and it's quick. And then, just because it takes a while, we grid all the channels. Here we go. So, and that thing, you know, then we have thorium, we have the raw, we have the background corrected window channels and the radon corrected, and then now we have potassium, uranium, thorium in ground concentration. So we want to have a look at the grids. So let's just, because there are plenty of grids in there, as you can see, we just run that for a moment. Run task file. Guys, what about your time?
I'm good. I can.
I'm good.
Stay.
Yeah, I can stay a little bit more if we go over time.
Cool. Yeah.
I need to leave in like 2 minutes, but that's okay. That's the part that you showed me is a part that I wasn't sure of and that I needed to learn. So thanks for that.
So you need to leave. You need to leave when?
Now, in 1 minute.
Oh shit. Okay, because
that's okay. I know all the, you know, from gridding onwards, I know how to do all that. So it was the first part that I needed to learn. So thanks.
Oh, okay. So then let's run task file. Just quickly check the uranium grids then only. We just calculated. So now we have to think the other way around, because Intrepid is the only software that looks at the bottom stack first. So this is basically the raw, this uranium channel, which is the problematic thing. And I'm not sure display what I'm doing. Come on. Oh yeah, okay. So that is the raw. That is background removed. Okay, so it does do something. Specifically, you look at thing at the bottom in the south. The radon removal and everything actually did do some good, because that's the raw data. There's something wrong. It didn't do anything here for that line, for instance, or those lines. So there's still something wrong. And obviously, the bottom one is the final uranium ppm. They don't look that much difference. There's a height correction in there, but there is not much height differences. So that's okay. Uranium channel is always the worst. The others look better. So but there is something wrong with the uranium, with the radon removal. Maybe we didn't do it correct, or maybe the spectra are not correct. Okay, so let's go to the extras, and now, because that is the point of discussion basically. If we look at that, this is swap presentation. So this is the sum spectrum of flight 2. Yeah, so there's the raw one in there and the energy calibrated one. Yeah, and so energy calibration works. So that is flight 2, and that's a different flight 17. Yeah, just one other flight, and you see that the raw is completely different from the other flights from flight 2. Okay, but we did do an NASVD smoothing on raw. Yeah? We did do it flight by flight, but there is a problem. There is within that survey, within those flights, there is a spectral shift in there. So we might have to have a look at the NASVD again. All right, and that is hold on, let me just kill those things here. That is where it comes to pseudo flight or manual pseudo flight. Yeah, the pseudo flight, as I explained, is just that is the automatic version. It's just a dB edit thing. Hold on, create pseudo flight is just a dB edit thing. It takes, in this case, 10,000 values, and it just creates a pseudo flight. the first 10,000 values are assigned to flight 1, and that is then input into the NASVD. And because you have to leave now, the pseudo flight, the automatic pseudo flight, doesn't work that well. It's worse than the flight by flight correction. And the reason for that, one of the reasons for that is the spectral shift from flight to flight. And the thing is, if you go to any statistics, just the line stats, then you do see the pseudo flight. This is pseudo flight 1, flight 2, flight 3, and there's flight 4, and there's more. But it takes the lines 11, 15, in consecutive order, but it's different flights here. 50, 33, if there's 50 again, 34, 49, is all taken into one pseudo flight. If we apply then NASVD, if you apply the principal component analysis or any principal component analysis regarding that pseudo flight, we mix the flights, and we've seen that, and that's in the extras in there. There are all the spectra, just screenshots from the sum spectra. We can run through them. So there's something wrong, and matter of fact, the standard straightforward creation pseudo flight NASVD smoothing creates not so good data as the first attempt. So what I was basically, I checked the all the calibration, the sum spectra per flight, and I just did a manual pseudo flight. You start false. Where is it? Hold on. On the wrong directory here. Let's see, per flight, create pseudo flight manual. So basically, here from flight smaller than 15 is pseudo flight 1, 15 to 18 is pseudo flight 2, and so on and so forth. And I did that basically looking at the sum spectrum per flight, and then the NASVD with the manual pseudo flights actually produces a smoother spectrum than the first one. And we would have to run through basically to get the best spectrum out to actually have a good radon removal. And that whole thing then, there was an old discussion 20 years ago. People were trying to take each crystal, the records for each of the 8 crystals, energy calibrate them first, then sum them up, and then do the NASVD, and the results were absolute marvelous, straight, clean spectra. However, energy calibration and spectral smoothing in the wrong order was not seen well by GA. So the system was banned from Australian government jobs, although it actually did produce the better data. And maybe nowadays the spectra are good. So you don't have the problems we have here in the Kukrad spectra, but it may well be worthwhile getting back to that discussion. What happens if one of the bloody crystals is drifting and the others are not? Can I apply an SVD? How many spectral components shall I use? Because if every of the 8 crystals drift in different directions, energy drift in different directions, principal component is nonsense. I get 8 by 8, we use 8 times 8, I get 64 principal components. That defies the purpose of spectral smoothing. But it popped up again with that Kukrad data because they're old. With the new data, you don't have that problem, or you shouldn't have that problem. Let's put it this way.
So is that simply just because the crystals we have are better, they're less prone to drift? Is that what you're saying?
No, it's the control over the crystals are better. I mean okay. Brian Minty and Jens Hofgaard from RSI are mates, and they're both of them on the very much on the theoretical side. So if Brian says that the energy calibration that is done internally in the RSI systems is correct, then it is correct. You know, they talk to each other, and they are both from the, you know, from the pure science side. So the RSI crystals, I didn't have that many, so I can't really say there is no problem. But the very few RSI spectra I had were absolutely freaking stable. You know, to the and yeah, to one of the 1024 channels. So the energy calibration in the RSI systems, as far as I can say, is good, and I would expect other manufacturers being at the same level. You know, whether you whatever Pico and Varatech or whoever else produces crystals. Before you go, I just want to say there's one thing which is basically full spectral modeling. It's a technique that stems from the Czech Republic or Czechoslovakia at the time, and it actually works. World Geoscience had that around the 2000s. You take a model spectra, and of 3 or 4 of them, and you basically do the whole processing thing, not the standard way. You just model the spectra. You know, you scale them up and down these square cents until you fit the input spectra, and the only one who is still doing that is a Dutch company, and they produce very small crystals, so you have to have a different processing technique, and it works well. It's just for you to know if somebody comes up with sort of as a spectral, instead of going through the full spectral analysis and scaling and smoothing and this and that and calibrations, and you can also model spectral modeling. You can also process data with spectral modeling, and the results are good. The thing with the Dutch company is they do generate the model spectra in the lab, so it's an absolutely controlled environment. That was the problem with the old World Geoscience data. They thought they could take a pure uranium or thorium spectrum out of survey data, which didn't really work. But as long as you have proper, clean spectra for that specific system and that specific height and all that thing you need to know, you need to have, because spectral shapes are changing with all different parameters. You can do spectral modeling. It's definitely worth a test. You know, don't if you sit there and you get a submission or a tender bid from a company who wants to do spectral modeling, don't just put them in the off bin. It's a good technique. It works, depending on how it is implemented.
That's good to know. Thanks.
But I'm not aware of any commercial contractor who actually uses that, just in case there is somebody pops up with that.
Okay.
So the Dutch company is creating small crystals, which are too small for standard airborne surveys. You know, it's a 4-liter crystal, and they do drone crystals, which are allowed only to weigh 1 kilo. So it's a completely different story. So they won't pop up in your standard GA surveys. That's basically it. And I thought, you know, these Intrepid training data sets, EBA, GULA S and EBA, GULA A, and whatever. I can't really hear the names.
Yeah,
so I thought,
thank you,
Cookrad. So that's Cookrad, and it's shit data. And actually, it's a good idea. It was good that it's not so good data, because it did show some problems that can crop up, specifically if you deal with old surveys or old survey data that was flown with the GRA20, which was you know, the standard at the time, but the standards at the time were not as good as the standards today. So that Cookrad data set actually does highlight a couple of potential pitfalls.
I thought that was a really good example. Thank you very much, Rainer. I appreciated going through all those task files as well, and just looking at the different visualizations. That's something that we haven't had a lot of in the past. So I got a lot out of just running through those. So thank you very much.
Yeah, no, cool.
Yeah, thank you.
Thanks for,
I think I'll be running the task by myself because I couldn't run it straight away. But yeah, it was really good. And by showing that data with some issues, we can see the improvement that he can bring to the data. So thank you. Thanks so much. Yeah.
Yeah, and don't worry. I've seen speckle plots with guidelines already, but it's not in your version. And I was told that your IT has a whatever you can't install every other day a new version, but it's already in Intrepid, because I think it's important that you know where the theoretical peaks are if you look at spec.
Oh, great! That was going to be my next question: is when do you think that'll come? Yeah, but for us, it's probably a few months away. We have to get things packaged, and they have to go through security, so that it'll just take a while.
Yeah, James, and I can say a few words about that. This radiometrics processing is now becoming possible for to improve. And as Rena said, every day there are quite a few improvements being added, and we'll try to streamline the workflow as well, and try to integrate, say, for example, several tools all together. I think probably just simply after a few months time, after several tests, we'll probably release a new one with probably how can I say, simplified a version with a simplified user interface, and make it much easier to use, get rid of some of the ambiguous items, that kind of thing. So I'll definitely let him know.
Fantastic, that sounds great.
Okay. Yeah. Thank you.
All right, then.
Any other questions? Yeah.
And have fun with radiometrics.
That's right. Okay, well, if this is the case, I can probably, I think we'll just conclude today's training session. And sorry.
And to you, to the two of you, if there is any problem, do not hesitate to contact me via email. Or
all right. Thanks so much. Thank you.
Zoom thing.
No, thank you very much, Ryan. I appreciate it.
Thank you, James, and thank you, Yevit. Thank you for joining us today. Okay.
Thank you too.
I'll see you tomorrow. Yeah.
Okay.
Thank you.
Yes,
and,
Bye.
have a nice evening.
Yeah.
Yes,
thank you. Have a nice day.
Yeah. Bye. Thank you.
Yes.
Thank you.
Okay.
Bye, everyone.
Yeah,
bye.
Bye bye.